Hi everyone. In this lesson we're going to go over multiple integration, and this is going to allow us to calculate volumes of solids that lie underneath a surface defined by an equation like z equals f of x comma y. Now before we get into the details of multiple integration, let's recall that from the fundamental theorem of calculus we have this result. We're going to make use of this a lot as we derive our formulas for multiple integration. So remember what this formula states. If you have a function that's defined over an interval AB, and you break this interval into n subintervals just by dividing it up, then the limit of the summation of these quantities. Now remember, these represent area of rectangles, as we'll see in the graphic down below. The xi is chosen from the ith subinterval, and the delta x represents the width of each subinterval. So when you take the limit as n goes to infinity, remember this summation here turns into an integral. The delta x turns into your dx, and the f of x sub I just becomes f of x. So this is from the fundamental theorem of calculus. Now just remember that this quantity right here, or in particular the f of xi times delta x, that represents the area of rectangles as we have down here illustrated. Okay, so right here we have the interval from A to B divided into, here we have 5 subintervals. The xi right here is chosen from the ith subinterval. F of xi represents the height of this rectangle, right? This distance is f of xi multiplied by the width. That gives you the area of this rectangle. And then we sum all of them up. And then we take the limit as n goes to infinity, where n is the number of subintervals that we have. So as n goes to infinity, these rectangles are going to get smaller and smaller, and they will fill in the area underneath the graph of this curve. And so we interpret this limit as being the area. That's actually what we interpret the area as equaling. The fundamental theorem of calculus tells us that this quantity in the limit, it will approach a single number L as long as f of x is continuous over the interval from A to B. And that number actually equates out to this number right here. And remember, this is equal to capital F of B minus capital F of A, where capital F is your antiderivative for little f. So in other words, where the derivative of capital F equals little f, right? Capital F is just your antiderivative. So make sure you understand this before we move into multiple integration and the derivation of it. Okay. Now, what we want to do with multiple integration here, we want to find out how to calculate the volume of a solid that is bounded above by some surface. So right here we have a surface given by z equals f of x comma y. So, this looks like it might be a paraboloid, could be something like 4 minus x squared minus y squared. Maybe it's, an equation like that, whatever it might be. And it's bounded below by this region in the xy plane. So we want to find the volume of the solid where the lower surface is this region in the xy plane, and the upper surface is determined by this function. Okay, so what we're going to do here is we're going to do something similar to what we did with the integral of f of x dx from a to b. We're going to break this region up into tiny rectangles. Now they're going to be two-dimensional rectangles. Over here, we broke the interval AB into little subintervals. Okay, so those were one-dimensional subintervals. When we break this region up, we're going to have two-dimensional little tiny rectangles, like we have illustrated down here. Okay, so you see in this graphic, what we've done is we've broken up the x-axis into some number of subintervals, and we've broken up the y-axis into some number of subintervals. And that breaks up the region R in the xy plane into these little rectangles right here. Now you notice that this point right here is located at position x sub I comma y sub j. Okay, so take note of that. Also notice that the width of the intervals along the x-axis, these subintervals, these have width delta x, so that's labeled right here. They have width delta x. Along the y-axis, these distances right here that we broke the y-axis up into, those have width delta y. We'll call that width delta y. And so the area of these little rectangles right here, they have area delta x times delta y. Right, so keep that in mind. And also notice that we have these bounding curves right here. So this bounding curve right here, we call that y equals g2 of x. It's just some function of x. And then we have another bounding curve down here. We call that y equals g1 of x. Now in this picture, of course, it's just y equals 0, right? It's just the x-axis. But it could be some function of x. It doesn't have to just be y equals 0. It could be some other function of x. So just keep that in mind. All right, now let's see how we can calculate the volume of this solid. So let's take a look at the next graphic. So down here, we have the volume of this rectangular box here written as the area of the base, which is delta x times delta y, times the height, which is f of xi yj. You see that point right here, that point right there, in the middle of that box, you can think of that point as being x sub I comma y sub j. Okay, and if we evaluate f of this number, that'll give us the height of this box. So the volume of this rectangular box is going to be area of the base times its height, and that's what we have written right here. So delta A is area of the base, f of xi comma yj is the height, and keep in mind delta A is just delta y times delta x. Okay, so we call the volume of this delta V sub ij, or I comma j. All right, so what we're going to do is we're going to add all of these up. That's going to give us an approximation to the volume, and then we're going to take the limit as these little rectangles get smaller and smaller, or the limit as we take more and more of them. Okay, so let's see what we end up with when we do that. Okay, so here you see we have written the volume as being approximately the summation of all of those volumes. You see the I is going to index from 1 to n, and the j is going to index from 1 to m. The n and m depend on how finely we partitioned the x and y axes. And the delta v sub ij is, remember, that's just this quantity right here, and which we can write like this. Okay, so keep in mind each one of these now represents a volume. And you notice we have a double summation here now. You see, we're going to sum over the j's first. So if we think of the I as being fixed at some value, then we're going to index over the j's, so that's going to increment us along the y-axis down here. So if we start out with I equaling 1, that's going to increment us along the first column like this, going along the y-axis. Then we jump over 1, let I be 1, we move over, and then we add up all the volumes of little boxes for, when I is equal to 1. Then we jump over again and let y increment, or let j increment, and so on. Okay, so you notice we have a double summation here now. Well, we need to take the limit as, the size of these little rectangles goes to 0, and we need to see what this turns into. Well, you can sort of get an idea here already, thinking back to the fundamental theorem. Both of these are going to turn into integrals. And you see, this is going to become a dy, and this is going to become a dx. So we're going to have like a double integral involved here. Well, let's see what happens. Okay, so right here you see we have that our volume is going to exactly equal the limit of this summation as the size of the little rectangles goes to 0, or you can think of the number of partitions of the x and y axes going to infinity. Okay, now keep in mind there's actually a double summation in here because I'm summing over I and j. And this delta A is delta x times delta y. Okay, now let's jump down here and see what this gives us in the limit. All right, so here we have our volume written as a double summation here, like we saw before, with the delta y times delta x. Now let's just note that, we can write it like this: the summation of the inner quantity right here, the inner summation, times delta x, so these two are the same thing. Now, by the fundamental theorem of calculus, if we let the size of our little rectangles go to 0, or the number of partitions of the y and x axes go to infinity, this right here is going to turn into an integral. That's going to turn into an integral with respect to y. And so you see the inner, what's inside here, turns into an integral from g1 of xi to g2 of x sub I, f of x sub I comma y dy. So that's by the fundamental theorem of calculus. You see, we're only applying it to the variable y. Now we're thinking of the xi as being held fixed. Okay, so where are these limits of integration coming from? You might be wondering, well, where are those coming from? Well, if you look back to the diagram that we have up here, Let's just go back up here. Let's go back up to this one right here. You see, with that inner summation, we're thinking of fixing the xi, and then we're going to increment over these rectangles first. So you see the y is going to run from g1 of xi up to this number on the y-axis, and that number is going to be g2 of xi. You see that? So you're going to go from g1 of xi up to g2 of xi. That's what the y is varying from, because we're initially thinking of holding the xi fixed. Okay, so that's where those limits of integration are coming from. Now let's go back down here. Okay, so we see that this just turns into this integral. And now, well, what's going to happen with this summation here? Well, it's also going to turn into an integral, and this is going to turn into a dx. So that's what we have down here. So you see right here is our volume. And now what we've determined is that the inner summation in the limit, it will turn into this integral. Now, if we take the limit as the size of our rectangles goes to 0, that's going to mean that the number of partitions along the x and y axes go to infinity. So then, if the number of partitions along the x-axis is going to infinity, this is going to turn into an integral, and this is going to turn into a dx. And any place in here we see an xi, we just replace it with an x. And so we end up with this result down here. Now you notice the delta x became a dx. Now our integral runs from a to b. Okay, why is that? Why does it go from a to b? Well, let's go back to that picture that we had up here previously. Let's just go back up here. So initially we held the xi fixed, and the y varied from g1 of xi up to g2 of xi. But then we have to think, okay, now what does the x vary from? Well, now the x is going to vary from this point on the x-axis to this point on the x-axis. So it's going to go from one number to another number, from a to b. Now in this picture the a is 0, but it could be anything. Okay? So that's a general rule that we're going to see, is that when you do a double integral, the first limits of integration on the integral, the first limits of integration on the inner integral are going to be functions. Okay, so if I'm integrating with respect to y first and then dx, these are going to be functions of x. And we say you go from curve to curve, and then the outer integral is going to be from a single point to another point. So curve to curve, point to point. That's how this is going to work out. Now we'll see later on you could switch the x's and y's, integrate with respect to x first and then y. Well, then you would have to change your curves down here. So you would have to think of these two curves first, this one and this one. You would have to think of this one as being x as a function of y, and this curve as being x as some function of y as well. And then the y is going to go from, say, like c out to d. So it would be like if you switch these orders of integration, it would go from h1 of y to h2 of y, and then from c to d. But we'll get to that later, okay? Let's just finish our discussion that we're doing here. So that's just a little foreshadowing there. Okay, so now let's go back down here again where we were. Okay, so right here we see that this double integral right here will give us that volume bounded between the region in the xy plane and the upper surface z equals f of xy. And that's exactly what we have written right here. Now here we have the statement for the volume of a solid, how to calculate it. Now there is one correction I have to mention here, and this should be corrected in your notes already. For the volume of a solid, we do want the f of xy to be bigger than or equal to 0 over your region in the xy plane. Just like, remember, if you have a function that looks like this and you calculate the area from A to B, like this, and you evaluate the integral from A to B of f dx, that's going to give you the sum of the signed areas. So this area would be positive, this area would be negative, and it would give you this area minus this area down here. That's what this would evaluate out to. Same thing for volumes. If your f of xy dips below the xy plane, then for the wherever the function is below the xy plane, that's going to have a negative volume. So this down here would equate out to the sum of the signed volumes. Just like up here you get the sum of the signed areas. So just keep that in mind. Okay, so anyway, here's what the result states. If we're given a positive function defined over a region, x comma y, where x is between a and b, y is between two functions, the volume of the solid bounded between R and the surface, the upper surface, z equals f of x comma y, is given by this quantity right here. Now we actually have to look at some examples to see how do we actually calculate that. It's not really that hard, so we'll look at an example soon where we calculate that. Now let's take one additional note here. Here's another way to view this formula, and this may help to help you to visualize it a little bit better. When we're trying to calculate the volume of this solid right here, here's another way to think of it. If you partition the x-axis like we have partitioned here, and you take a thin little slab, you see this slab right here that we've taken. Now that slab has a width delta x. The area of this slab, right, so this area right here, the area of the side of that slab, is going to be the integral of f of xi, where the xi is fixed, comma y. Integrate that with respect to y from g1 of xi to g2 of xi. So you see what this inner part of your integral right here is giving you. You can think of it as being like the area of this slab, the side area. That's what it's giving you. And then when you multiply it by delta x, that's going to give you the volume of this slab. And then you sum up the volume of those slabs, and you get an approximation to the volume underneath the surface z equals f of x comma y. And when you take the limit as the number of partitions on the x-axis goes to infinity, this turns into an integral, this turns into a dx, and the x goes from a to b, and you end up with the result that we had up here previously. So that's another way to view this quantity, the integral here times delta x. You can think of that as being the volume of this slab that we have pictured here. And then we're adding up the volumes of all these slabs and taking the limit as the number of partitions along the x-axis goes to infinity. So that's just another way to view it. Now let's take a look at an actual example. Okay. So here we want to find the volume of the tetrahedron formed by the planes x equals 0, y equals 0, z equals 0, and above by this surface. So that's just a plane. Okay, now down here we have pictured the volume that we're actually trying to find. So right here it is. Okay, so you see the lower region that I had, the R right there, that's where z is equal to 0. This side right here, that side is y equals 0. The side over here, that's x equals 0. The R is z equals 0. And then the surface, you know, this triangular part right here, that's your surface. Z equals 6 minus 3x minus 2y. Okay, so we're trying to find the volume of that tetrahedron. Okay. Now let's note this. This curve right here, we find the equation of that curve by setting z equal to 0, right? Along this curve in the xy plane, that's where z is equal to 0. So if we put a 0 right here for the z, put a 0 right there, solve that for y in terms of x, this is what we get. We get y equals negative 3/2 x plus 3, right? Just take the 2y over, divide by 2, and you get this. Or if you solve for x in terms of y, you would get that. We'll use this later on. Okay, now let's just set up our integral right here. We can see how we set this up. So our volume is going to be given by, okay, so we're going to have, that's our surface, that's our function f, so it's going to be 6 minus 3x minus 2y dy dx. Now let's think, what are the limits of integration going to be for our first inner integral? Well, if we think of fixing the x first, so x is held fixed right here, y is going to vary from this curve, which is y equals 0, up to that point on the y-axis right there is negative 3/2 x plus 3. You see, it's dependent on where this x is. So up that point right there on the y-axis is this quantity. It's dependent on x. So it's going to be negative 3/2 x plus 3. Then, what does the x vary from? Okay, now what is this x allowed to vary from? Well, it's going to go from 0 up to 2. And there you go. You have your double integral set up. That will give you the volume of that solid. Now let's see how we actually evaluate that. Okay, now we have to evaluate it. So, well, let's move down here now. We have it down here. Okay, this is just some explanation of what I just said. Okay, so right here is where we evaluate it. So right here is the double integral that we just set up, right? Inner integral, curve to curve, point to point. Okay, now what we do is we integrate this with respect to y first. So anywhere you see an x, you treat that like a constant. Antiderivative of 6 is 6y. Antiderivative of 3x is 3xy. 3x is just like a constant. Antiderivative of 2y with respect to y is y squared. Evaluate that from 0 to negative 3 halves x plus 3. So anywhere you see a y down here, you put in this, and then minus, and then you put that in for y and subtract the 2, right? So here we go. Let's do that. So you see right down here, this first part right here is where we put negative 3 halves x plus 3 in for all the y's. And then we put 0 in for all the y's, and we get this 0 right there, of course. And now we just need to simplify this. It's just a bunch of algebra. You know, you have to FOIL this out. 3x times negative 3 halves x, and minus 3x times 3, and, you know, it's just some algebra. This is all just a quadratic in here. You just need to simplify it. And I claim that you will get this down here. So I'll let you work that out. That's just some algebra that you normally have to go through with these problems. Now you see this is a regular old integral with respect to one variable that you've all seen before. Now you just have to evaluate it. Antiderivative of 9/4 x squared, that's going to be 3/4 x cubed. Antiderivative of 9x, 9 halves x squared. Antiderivative of 9, 9x. Evaluate from 2 to 0. So, of course, you put the 2 in for the x, 0 in for the x, and subtract, and I claim you will get 6. I'll let you verify that. That's pretty easy to do. You should all know how to do that. And there you go. That's how you evaluate a double integral. So once again, you know, just to summarize here, the inner integral, we had to integrate this with respect to y, treating the x like a constant. So there it is. Then we use our limits of integration. Now they're going to be functions of x, so you have to be careful. These go in for all the y's that you just integrated with respect to. Then you get just a function of x, and from there it's just a regular integral with respect to one variable that you do. And that's it. Now in this example, we integrated with respect to y first and then x. Now, as I alluded to before, you can change this order of integration. You could integrate with respect to x first and then y, but you would need to change your limits of integration then. Let's see how we would set that up. So let's go back to the diagram for this problem. All right, so we saw that if you integrate with respect to y first, your limits of integration are going to be from 0 to negative 3 halves x plus 2. That's what the y varies from. And then x is going to go from 0 to 2. Now, if you change the order of integration, let's see what's going to happen to our limits of integration. Well, now what we're going to do is we're going to think of, when we evaluate the inner integral here, we have to think of the y as being held fixed first. So if we look at this picture over here, this diagram, if we hold the y fixed, then x is going to vary from this curve, which is where x is always 0, up to that point right there. Now that point depends on what y is chosen to be, and it's given by the equation of this curve, and you see x equals -2/3 y plus 2. So this point right here on the x-axis, that is going to be the point -2/3 y plus 2. All right, so it's going to be that right there. So the x, if we hold the y fixed first, the x is going to vary from 0, it's always 0 along here, up to -2/3 y plus 2. Okay. And you see all we really did here was we took the equation of this curve right there, which we had as y as a function of x, and just solved for x as a function of y. Now, with the outer limit of integration, we have to then ask ourselves, okay, what does this y vary from then? Well, the y goes from this point on the y-axis, which is 0, up to this point on the y-axis, which is 3, right? So 0 to 3, like that. And once again, you get that 3 just by putting 0 in for this into this equation right here, and you get y equals 3, of course. And so both of these double integrals will give us the exact same number back. And just to verify that, let's take a look at evaluating this right here and see that we do get the same number back. We had better, or else there's something wrong with what we've done. So if we go down here to this example, so reversing the order of integration is what this example 4.1.12 is asking us to do with that problem. And right here you see we have it set up right here. Notice we integrate with respect to x first from 0 to -2/3 y plus 2, and then y goes from 0 to 3. Now when you evaluate the inner integral first, now you need to integrate this with respect to x, thinking of the y's as being constants. So the antiderivative of 6 is 6x, antiderivative of 3x is 3/2 x squared, antiderivative of 2y, now that's like a constant, is 2y times x. Then the limits are as we have here. Now when we evaluate this, anywhere we see an x, we have to put in this and subtract, right? So putting -2/3 y plus 2 in for each x, you get this right here. There you go. And then putting 0 in for all the x's, you just get back 0. And there you go. Now this integral is just another integral with respect to a single variable. Simplify this in here. Just, FOIL everything out and combine like terms. You end up with this. And then just evaluate the antiderivative of this Oops, and there is an error right here I just noticed. This should be a dy. You see that? That should be a dy right there. That should be fixed in your notes. That's a dy, of course. That dy carries down. And we need to integrate this with respect to y. So, of course, you get 2/9 y cubed minus 2y squared plus 6y, evaluated from 0 to 3. Put 3 in for y, 0 in for y, and subtract, and you can verify that you will get back the same thing that we got back before, which is 6. So there you go. That's how you can change the order of integration. And that is essentially what Fubini's theorem here is stating. That's the statement of Fubini's theorem up here. You see, Fubini's theorem is making the statement that you can switch the order of integration and you will get the same answer as long as, the region defined by these two limits of integration like this define the same region. In other words, as long as the r here and here do define the same region, you are allowed to switch the order of integration. Once again, notice the inner limit of integration here, curve to curve, when we're integrating with respect to y first, these are functions of x, because these need to be functions of x so that when we perform the outer integration, everything is in terms of x. Now over here, we're integrating with respect to x first, so these need to be functions of y so that the outer integral, the integrand, is going to be completely in terms of y. Okay, let's take a look at another example. Now let's take a look at this example. So here we want to find the volume of the solid bounded between the surfaces z equals 0. Now that's the xy plane. Y equals the square root of x. Now that's a curve in the xy plane, but if we think of in 3 dimensions, it'll form a sheet as it comes up out of the xy plane. Y equals 2x. That's another curve in the xy plane, but it forms a sheet when it comes up out of the xy plane. And then z equals x squared plus y squared, that is a paraboloid, right? Now down here we have a graphic of the volume that we're trying to find. So you see right here, that is the curve y equals 2x. This is the curve y equals the square root of x, so they come up out of the xy plane vertically until they hit the upper surface right here and over here, until they hit the upper surface z equals x squared plus y squared. So we're trying to find the volume of that shape right there. Okay. Now let's set up our double integral. So let's take a look at this graphic we have below here of the region R to figure out what our limits of integration are going to be. So here we have our region R. Now here we have our double integral set up. So you notice if we integrate with respect to y first, we have to think of the x as being held fixed. Then the y is going to vary from this point on the y-axis up to this point on the y-axis over the region R, you see. Now this first point right here, since y equals 2x, well, that's going to be 2x on the y-axis. And for this curve, y equals the square root of x. So that's going to be the square root of x. So our limits of integration with respect to y first are going to be from 2x to the square root of x. Then we have to think, what does the x vary from? Well, the x is going to go from this point, that's clearly 0. In other words, we're asking, where does the square root of x equal to x? That's what we need to find. Well, obviously 0 is one solution to this equation. And then the other solution to this equation is going to be when x is 1/4. That's going to be right here on the x-axis. And of course you get that just by solving this equation for x, square both sides. And of course you see you get 0 and 1/4. So then this x right here that we held fixed initially, it's going to vary from 0 to 0.25. And we have that right here and here, or up here and here. Okay, so now we just have to evaluate this. All right, and when we do that, we need to integrate this with respect to y first, so we treat the x like a constant. So the antiderivative of this is going to be x squared times y. X squared is like a constant, plus y cubed over 3. And then we need to put in the square root of x and 2x in for the y's and subtract. So here we go. This is with the square root of x put in place of the y. So you get y squared times, so you get x squared times the square root of x, that's x to the 5/2, plus, and then when you put the square root of x in here for y, you get x to the 3/2 over 3. Then when you put 2x in for the y's right here and here, you will get this. Now you just need to, if possible, simplify this, combine like terms. Of course, you can combine these two terms right here, and you will end up with this down here. Now this is an integral only involving one variable, and you can just integrate it. Antiderivative of x to the 5/2 is 2/7 x to the 7/2. Antiderivative of this is going to be 1/3 times 2/5, so that'll give you 2 over 15 x to the 5/2. Antiderivative of x cubed is x to the 4th over 4, and you need to multiply that by 14 over 3. You'll get 7 over 6 x to the 4th, and then put in 1/4 and 0, and this is what you end up with. 0.0018415. Okay, so that's how you do that, integrating with respect to y and then x. Now let's flip the order of integration and see that we get the same thing. Now down here we have the same problem set up, but with the order of integration reversed. So now we want to integrate with respect to x first. So we look at our diagram over here, and now we think of the y as being fixed. That's our outer integral. That's what we're integrating with respect to last. So we think of that as being held fixed, the y as being held fixed. And we have to think, what does x vary from? Well, x is going to vary from, if we drop this point down, it's going to vary from that point, and we go over here and we drop that down to this point. Now those points, this point right here lies on the curve y equals the square root of x, or x equals y squared. So this point right here is going to be y squared. This point lies on the curve y equals 2x, or x equals y divided by 2. So this point down here is going to be y over 2. So those are going to be our first limits of integration with respect to x first. So the x is going to vary from y squared to y over 2. Notice we go lower to upper, lower curve to upper curve. Then this y was initially held fixed. Now we have to think, what does it vary from to get our outer limits of integration? Well, we can see it's going to vary from that intersection point up to this point right here on the y-axis. Now, what is that point? Well, we already found out that these two curves intersect when x equals 0 and x equals 1/4, right? We already found that out. So if I put 0 into either of these equations for x, of course I get back y equals 0. That's down here. And if I put 1/4 into either equation, we get back 1/2, right? So that's going to be that point right there, 1/2. Okay, so the outer limit of integration are going to be from 0 to 1/2. And there we go. Now we're set up and we can evaluate this. So we integrate this with respect to x first. Treat the y like a constant. Antiderivative of x squared is x cubed over 3. Antiderivative of y squared is going to be y squared times x. Y squared is just a constant when we're integrating with respect to x. Now we just have to put y squared and y over 2 in for the x's in here and subtract. Okay, so this y over 2 goes in place of this x and that x. We get this. Y squared goes in place here and here, and we get that. Right? Y squared in here, y squared cubed is going to be y to the 6th power. Y squared times y squared, that's going to be y to the 4th, right? Y squared times y squared. Simplify this a little bit. Let's see, we can of course combine these two terms right here. That will give us, well actually I don't have them combined down here, I still have them separated, but of course we could combine those if we wanted to. If I add these together, I would get y cubed times 13 over 24, right? 1 over 24 plus 1/2 is going to be 13 over 24, okay? Now, integrate this with respect to y. You're going to get negative y to the 7th over 21. That's the antiderivative of this piece first. Antiderivative of this is y to the 5th over 5. And the antiderivative of this is going to be y to the 4th times 13 over 96. Put in 1/2 and 0 in for the y's, subtract, and you will get the same result that we got previously. And there you go. So that's how you set this problem up with respect to two different orders of integration. And finally in this lesson, we're going to consider the average value for a function of two or more variables. Now recall from Calculus 1 that the average value for a function of a single independent variable over an interval from a to b is this. It's 1 over b minus a times the definite integral from a to b of f of x dx. And keep in mind this value right here in the denominator, b minus a, of course, that's just the length of the interval over which you're integrating. And so if you have a function, that looks like this, the average value is It's literally the average of the f of x values over the interval from a to b. If you were to think of the area underneath here as being a thin film of water with this as the boundary, and you remove that boundary, the water would slosh down to an average level. So it would look like this, right? And this height would be your average value. That's what this quantity would evaluate to. Okay, so that's the average value for a function of a single independent variable. Now, what we need to do is generalize this to a function of two variables. Well, it makes sense that this is going to turn into a double integral over a region R. Now, what do we do with this right here? Well, this represents the length of the interval over which you're integrating for a function of a single independent variable. So it makes sense that when we go to double integrals, this should represent the area over the region R that you're integrating. And that's exactly what we have in our definition down here. So let's take a look at that, and then we'll look at an example. So here's our definition for the average value for a function of two independent variables. If we have a region R in the xy plane, and that region R has an area A, then the average value of an integrable function f of xy over R is this quantity right here. So you see, once again, it's just our double integral over R of f of xy, and we multiply by 1 over the area of the region R that we're integrating. This A right here, the area of the region R, is playing the role of the B minus A that we had seen in Calculus 1 for the average value of a function of a single independent variable. And so that's it. And let's take a look at an example. So here we want to find the average value of this function, 1/2 x times y, over the rectangular region, the set of points in the plane where x is between 0 and 4 and y is between 0 and 3. So let's take a look at this picture down here. So this is the region in the xy plane over which you're integrating. It's just a rectangle in this case. Notice x varies from 0 to 4. The y varies from 0 to 3. And this is what the graph of 1/2 x times y looks like. So what we have to set up here is our double integral of our function times 1 over, now the area of this region, this is a rectangular region, so it's pretty easy to calculate the area. It's of course just going to be 4 times 3, or 1/12. Now our limits of integration, those are pretty easy in this case as well, because we have a rectangular region. So our first limits of integration, curve to curve here, if we think of holding the x fixed, so we pick an x value here and we hold it fixed, we see that the y is going to vary from this curve, which is y equals 0, up to this curve, which is y equals 3. So it's pretty easy in this case because it's a rectangular region. So 0 to 3, remember we think of those as the curve y equals 0 to the curve y equals 3. And then our final integration here with respect to x, this x right here can vary from 0 to 4. And there we go. That's how we set up the average value for this function over the rectangular region that we have displayed here. Now we just have to evaluate this, and that's what we're doing over here. So let's take a look at that. So here, of course, we have to evaluate the antiderivative of this first with respect to y. So we treat the x like a constant. So that's going to be 1/4 x times y squared, right? The x is just like a constant. So antiderivative of y is y squared over 2. Evaluated from 0 to 3. Put 3 in for the y. Remember, we put these values in for the variable that we just integrated with respect to. So they go in for the y. So you're going to get, when we put 3 in for this y, we're going to get 9/4 x minus, and then putting 0 in here for y, we get 0, of course. And then we just need to integrate this with respect to x. That's pretty easy. We're going to end up with antiderivative of x being x squared over 2, of course. And just note that 1/12 times 9/4 gives you 3 over 16. Evaluate this from 0 to 4. 4 in for the x, 0 in for the x, and subtract, and you get 3/2. And there you go. That is your average value. So the average value for this function that we have pictured over here is 1.5, which is about right there on the z-axis. Now, if we form a box with base being the region R and height being 1.5 like this, let me just draw that in here. So here we have a box that is of height 1.5 with base being the region R. Now the volume of this box, of course, is going to be the area of R, 12 times 1.5. And of course, that is going to be 18. Okay. So what we're saying now is this 1.5 right here represents the average value of this function, this surface, over the region R. So the volume of this box, which is 18, is the same as the volume of the solid that lies beneath this surface and above the region R. So that's what this average value represents. It's the height that you need so that the volume of this box is the same as the volume of the solid that lies underneath this surface and above the region R. Okay, so that's what your average value is. And once again, if you want, you could think of this as being the solid as being water, and the surface as being a membrane. If you were to remove this surface, the water would slosh down and perfectly fill this box to this height, 1.5. All right, so that concludes this lesson about double integrals.